evening, good afternoon, and good day from the Radiant Professionals Alliance. Welcome to HydroniX Talk, a presentation of the Radiant Professionals Alliance. I am Mark Eatherton. I'm your show host. There's a little bit of information on me. I'm currently the Executive Director of the RPA. I've been a member for the last 20 years. I'm also a contributing editor to Contractor magazine, Plumbing and Mechanical magazine, and numerous other magazines that just pop up on my radar screen and say, write us an article. I've been an educator for 39 years. I'm a former expert witness and still a licensed master plumber, although I don't share that information with too many people because when I do, they ask me to come fix their plumbing. Here's some real quick rules of the road. If you would please use headphones and boom mics, if possible. That will avoid us having any kind of feedback or squelch going on during the presentation. If you have a question of our presenter, please enter a question into the typing Q&A text box, and I've already got an agreement with our presenter that he will stop at any point in time and I'll ask him the question and he can answer that question live as opposed to waiting until the very end. Questions regarding the presentation may be responded to after the presentation. When we're completely done, if you've got a question that has nothing to do with what we're talking about, but you would like some input, feel free to ask it. That's what this is all for. We appreciate you taking the time out of your busy schedules to come and attend this show. A little bit of history on myself. I'm a big fan of non-conventional radiant hydronic heating systems. This is a radiant wall heating system that we performed for Habitat for Humanity back about 20 years ago. If you go to the Department of Energy's website, you will see a picture of this same wall. That's because the DOE was one of the sponsors on this particular project, and worked with them and the good folks up at the National Renewables Energies Laboratory in getting the system up and running. There's the radiant ceiling in my home up in the mountains when it was still in its rough state. Love the comfort that comes from that. There's nothing greater than stepping into a room with a good radiant ceiling and it feels like you've got sun shining down on you, even if it's extremely cold outside. Here's the only advertisement that you will see during this presentation. We would ask that if you are not yet a member of the Radiant Professionals Alliance, that you join us. This is an organization of the members, by the members, for the members, with all of the members benefiting from all of our actions. We have a whole lot of stuff going on, and we're basically in support of hydronic industry in general. Give you a little bit of information about our show. This is, once a month we have guests that we bring on to the show and we interview them. I have an open Q&A session following the interview that doesn't have to pertain to the presentation. These shows are archived for our members only for review at a later date. If you are not a member, you won't be able to gain access to them at a later point, but if you join, then we can give you the keys and you can go in and look at all the shows that we've got up there, which we've got a pretty substantial gathering of shows that we've developed over the last couple of years. These shows are meant to be fun, educational, entertaining, and oh, did I mention fun? If you have a person that you would like to submit as a guest interviewee, by all means send them to me at mark.eatherton@radiantpros.org. Give you some real quick hydronic news that you can use. And by the way, if you've got news that you would like for us to share, send that to me and I will include it in our presentation. We have the RPA University spring course offerings, which are currently available. You can view them at heatspring.com. We've got Dave Yates up there, Ray Wolfarth. We've got a whole bunch of people that are teaching a lot of really good classes up there. Some of the classes that we're offering up there will be the basic requirements for people that are interested in becoming certified, which is one of the programs that we have through ASSE for either a hydronic system designer or installer. If you have any questions in that regards, again, please send me an email and I'll be glad to answer your questions for you. The Canadians are having a good old get-together. You speak Canadian, eh? Molson, yes. March 16th, 17th, and 18th at the Metro Toronto Convention Center up in Toronto. And I know for a fact that Robert Bean and John Siegenthaler are both going to be there. They're going to be doing a Siggy and the Bean presentation, which is always very interesting, very lively, and you'll come away learning something from it, I guarantee you. So quickly, this is the only point in time when I have to worry about the lawyers. The graphic and illustrations used in these webinar presentations are presented for educational purposes only. RPAI Atmo does not endorse or recommend the vendor products depicted, nor any vendor or product. RPAI Atmo makes no presentations, representations, warranties, or guarantees as to and assumes no responsibility for the products depicted, and RPAI Atmo expressly disclaims all liability for damages of any kind arising out of the use of performance of the vendor's products and or services depicted. Enough of the lawyers. Mr. Al, I'm going to transfer the ball of power to you and let you take over. Ladies and gentlemen, welcome Al Wallace.
Thank you, Mark. I have a little bit of a cold, so if you hear me coughing in the background, I apologize for that. This is probably a 90-minute presentation that we're trying to cram into 60 minutes. So I'm going to be moving a lot faster than you may feel comfortable with. If you think I'm going too fast, please let me know. But what I want to discuss is how to do radiant floor cooling and heating, and primarily with ground source heat pumps, but you could actually do that with the boiler chiller combination, just not as efficiently. Switching screen. I'm trying to page down and it's not going forward.
You may have to use the buttons up there at the top by the slide selection.
Up here, you mean? Yesterday at work, normally, no.
Yeah, no, a wonderful thing. Here, I'll move it for you. You're advanced now, Al.
I still show the same screen. How do I get rid of my eraser? I get rid of my notes. I'm sorry. So I'm not advancing. I'm trying, but I'm not advancing slides, Mark.
Can you see the overview on the screen now?
At the very top?
Yes, it's your slide.
Yeah, I can see my slide.
Okay.
I'm just not, it won't advance. Like yesterday, we practiced page down or page up.
Yep.
Or arrows.
It's probably a software problem, but you let me know when you want and I'll advance the screen for you.
Okay, just make the slide go forward. I'm not sure this is going to work that well. We have to keep doing this.
I've got your second slide up now. I'm actually on slide 16.
Okay, my screen is showing the opening slide. I don't know what everybody else has out there, but I do not show the slide number 2.
Let me take the ball back and I'll send it back to you again and see if that makes a difference.
Okay. All right, thank you. Okay, now I have the second slide up.
And you now have the ball of power.
So I'm still having a problem advancing slides, so I don't know what's going on. But okay, so we want to talk about efficiency of water over air, and comfort is the driving factor of radiant floor cooling, and I'm going to talk about systems design, so I need the next bullet to come up. Mark, this is
bullets up now.
I don't have anything on my screen. I just have the overview with one bullet.
Well, that's strange. Rich, what are you saying? Rich, you're unmuted. Can you tell me what you're saying?
Right now, number 16, Mark.
With 3 bullets?
Do you see 1 bullet or 3?
I see 1.
Right, that's what I see. So, Mark, for some reason, the people that in watching this, including myself, only see 1 bullet.
Oh, wait a minute. Pardon me. What's bullets, Mark?
The square blue dots to the left of the...
Oh, yeah. Nope, 1.
Just 1.
Just 1.
Well, that's bizarre. We're having a technical issue here. Let me...
We have a glitch.
We have a glitch. Houston, we have a problem. Tell you what I'm going to do. I'm going to unshare.
So while Mark's figuring out the slides, I just want to give you a background of how we got to the point where we got to. And essentially, 15 years ago, our company was doing integrated systems with radiant hydronics and ground source heat pumps. And one of the things we started getting into was the potential of doing radiant floor cooling, but we could not find an available control that was easy to use. And as you'll see in the presentation, Upener came out with their CCN system, which was a DDC interface, and they abandoned that about 4.5 years ago because it was very difficult for contractors to use, and it was also not supported well. But what we ended up doing with that system is we ended up modifying it so it would be radiant for cooling, and that's been installed in my house for the last 8 years. And we've learned a lot from that, as well as dozens of installations where we now use radiant cooling. Do you want me to test it now, Mark?
Yeah, give it a shot. You've got control now. I'm seeing full screen with 3 bullets up.
Okay, so I'm one page down. Okay, here we go. All right, cool. Great.
Second
Okay.
bullet's up.
Yep.
Okay.
So my control's working. Okay, so we're going to talk about radiant cooling requirements, and then I'm going to talk about control requirements. And they are completely different. It's really easy to send chilled water through the floor, but to do it correctly, comfortably, and not get a lawsuit on your hands is a challenge. And then I'm going to show some example installations that our company's done. If you're logging continuing education units, these are the learning objectives. There's some advantages for efficiency, and they're really related to systems configurations, which it's kind of very obvious when you see what those are. And then I would like to convey what you have to do as a minimum to do radiant floor cooling, as far as sensors, humidity, dew point, water flow, supply temperature, etc. And then a sequence of controls for implementing a radiant floor cooling and heating system. I'm going to talk about some intellectual property that our company has in our control, and the whole idea was get a plumber with a number 12 screwdriver that doesn't know any programming, and they should be able to implement a system like this, and that's really essentially what we're doing with the examples that we show you on the bottom. So air versus water, if you're in the hydronics business, you know this. A 1.5-inch pipe, you can send as much energy as a 2-foot duct. When you look at the actual savings of a radiant cooling system over a VAV system, it ends up being about 43% savings. This is a study that was done 20 years ago. Essentially, it's really the fan motor and the lights trying to move air versus circulator. And this is before we had variable speed pumps and other things that are even highly efficient at moving water more effectively. I've got 4 charts like this. Our company's actually developed hundreds of these. We use a data logger on our homes, and there's 3 takeaways that I want to get across on the next couple of slides. The first one is, with a forced air system, you might have a fairly constant temperature, which you see in red. That temperature is varying between 67 and 70 degrees. But it's that humidity that's going up and down. Every time that air conditioner turns on, and this time it's 8 to 10 times a day, so it is sized correctly. It's not short cycling. It's going to dehumidify that air, and when it gets dehumidified, and cooler, it feels cold, but then it gets clammy and warm, so it's not that comfortable to the homeowner. But the other key point is that the dew point in all these slides never gets over 57 degrees, and that's going to be important when we take a look at what our supply water temperature is in the radiant cooling system. This is what you would have if you have a winter makeup air boiler or furnace in the basement, and it's sucking in cold air. You're getting outdoor humidity coming into the house as the system operates, and the temperature varies greatly in the basement. But you'll notice, again, the dew point is still 51 to 57 degrees. It's kind of surprising. You would think that the dew point would be a lot higher or a lot lower. This is measuring solar heat gain inside a 1-inch pane of glass, or 1 inch inside the pane. And you'll see the extremes that the building envelope is subjected to when you have direct solar gain. And one of the things you're going to walk away from this presentation is understanding that a radiant floor cooling system has the ability to dramatically suck heat out of a floor that's directly lit by sunlight. So if you have infrared, long-wave radiation coming off the sun shining directly on an atrium or a floor, the radiant system probably can pick up 20 to 25 BTUs per square foot. You would never design for that, but long-wave radiation is what makes the space uncomfortable, and also, as we see in Colorado, it's one of the reasons clients say the radiant floor system's not working, it overheated, and it's at 80 degrees at 10 o'clock in the morning. Well, it really had nothing to do with radiant floor. It turned off at 8:30 a.m. It had to do with the radiation from the sun heating up the space. Again, looking at the dew point with these dramatic extremes, it's still below 52 degrees. This is a radiant floor cooling system. The first 4 days, the master bath fan was allowed to be left off, and you'll see that almost immediately when you take a shower, you're going to get an increase in relative humidity. Even though the dew point doesn't go up substantially, one of the things that you're going to see as a requirement is that you need to make sure on any radiant floor cooling system that you have constant ventilation in the building, and that you never directly cool a bathroom. So if you have the ability to take showers or baths, then those rooms are heat only, and you pick up any cooling loads with a supplemental cooling system, which I'll talk about in detail. Again, you can see the dew point with the bath. It's 51 to 57 degrees, and if the bath fan's left on, then it's 51 to 55, which gives me a comfortable operating range to do cooling. If we're not doing whole house dehumidification, then this is a chart that would give you a general idea how well radiant floor cooling works, just by ambient air temperature and humidity. So in the Midwest, or say Phoenix, Arizona, where it's really dry, you have excellent potential to use it in California. And you get down to the Gulf states or eastern U.S., that warm, humid line is where it gets tougher to do radiant cooling without whole house dehumidification. Now, some contractors or homeowners have mentioned to me that work in this area and say, we don't really want to install dehumidification. And the reality is, by National Jewish Airborne Allergies and Building Sickness Syndrome studies, anything over 50% is asking for mildew, mold, bacteria, and airborne allergens, which cause breathing allergies, which is a sick building syndrome phenomenon. Anything below 40% humidity leads to dry air, sinuses, eyes, and things like that. So 40 to 50% is really where we're striving to maintain the indoor air quality anyway. And you'll find that very tight homes tend to do that naturally, because without a dehumidifier, they tend to maintain the humidity in the house fairly constantly. Now, why would you put radiant cooling in? According to ACHR News, last year, 1/2 of all net zero energy buildings are using radiant cooling, and their motivation for that is basically to reduce energy. That comes down to the first slide I showed you, where water is 700 times more dense than air, so it's easier to move it around. It's also more efficient. But in residential applications, the driving force is comfort. Our company does 95% of our business in the residential world, even though we've consulted with and done commercial projects. It's the residential comfort that's driving the demand for radiant cooling. This is the Fort Carson Barracks. It's a net zero energy project to house 1,000 special operations forces in Fort Carson in Colorado Springs. I was a consultant on this project, and you will see that radiant cooling requires you to have PEX tubing 6 inches on center and also embedded in a high mass floor. You can't use warm board or staple down or staple up or any kind of a low mass system if you want radiant cooling. It just doesn't work as well. In my house, we actually have an area that we did as a low mass system when we do radiant cooling. And it's very uncomfortable with large temperature swings when compared to a high mass system. The other thing I want to point out about this Barracks project is that that open area in the center is not an area where they haven't finished it yet. That's kind of the bath and the kitchen area, and they have no intentions of putting tubing down. As you'll see, the ability to cool a floor when you don't have it 100% covered is a problem. Getting enough BTUs per square foot removed from the floor. And so in this case, it required supplemental fan coils in the ceiling. And what they did was they circulated water through the fan coils first above dew point, and then they circulated it through the floor. Another way of doing that to remove the latent load would be if you circulated water below dew point, in which case you'd have to have some kind of condensate drain or fan coil that was designed for cooling. Since this is a large commercial project with a DOAS, they can maintain the humidity at 50% and the system works. So we're going to talk about system design for just a second. This should be very intuitive to all of you that do radiant as a living. In this case, I've got a boiler and a supply. A thermostat calls. It basically goes to the zone valve controller, which opens the zone valve. And when the end switch opens, then it turns on your circulation pump. Kind of a no-brainer. 95% efficient boiler altitude in Colorado. Doesn't have the efficiency it does in Tennessee. And so we have to derate it for altitude. But your coefficient of performance is the kilowatts out divided by the kilowatts in. And in this case, I'm getting less energy out of the system than I'm putting into it. And you're going to see that with the ground source heat pump or some alternative configurations, we can dramatically improve that efficiency. This is a heating-only system, but if I take the exact same system and I use a hot tank, cold tank, I can make it a heating or cooling system. The question becomes, what's the coefficient of performance? And it really depends on how I'm making the cold tank cold and the hot tank hot. If I have a boiler and a chiller, that's going to be different than if I use the ground source heat pump. But again, yes.
We had a question. This goes back to your other slide with the high mass. This question is, ceilings require a low mass system. What's your experience with those? I mean, obviously the flywheel mass effect of the concrete is very beneficial, but most of the radiant ceiling cooling panels that are on the market are not a high mass consideration, with the exception of a couple of Euro systems that have literally got to be plastered into the ceiling itself. Is it just a function of being in contact with an extremely cold, low mass surface that creates the issues, or what?
It's a great question. There's actually 3 parameters that I can think come to mind. One is, if you have the ability to do above dew point cooling from the ceiling, that's more effective than doing it from the floor. So if there was a way, like in this application, let's say that the high mass panel that they're putting this into was the ceiling of the floor below it. If that entire panel was uninsulated, it would actually provide pretty effective cooling to the area below it. The low mass systems for radiant cooling, like chilled beams, usually have condensate drains, or they have some kind of collector for condensation. And that creates its own unique problems. What do you do with condensate? How do you maintain it, or whatever? If you supply the ceiling, like in this place, there's a Taco product that they put in there, and they're putting water through that ceiling panel above dew point, so they don't have condensation, but it is effective at removing cooling. It's kind of like your house mark, where you put all the radiant tubing for heating all over the ceilings and the walls. Mm-hmm. It still works really well, It's just a little more complicated to install that way.
Okay, thank you.
Our company doesn't have a lot of experience installing systems like that because we've done it with the configuration I'm about to show you here. Okay, so now let's fast forward and say, how do we make the cold tank cold and the hot tank hot? A typical geothermal heat pump takes heat out of the ground, go through a vapor compression cycle, and put the heat into the hot tank. If it's cooling, it takes the heat out of the cold tank and it puts it in the ground and it heats it up. So in the summertime, you're making the ground warm. In the wintertime, you're making the ground cold. And because it's kind of a temperate temperature in the ground, medium grade temperature, 50 to 60 degrees, it's a lot more efficient than your typical air conditioner. So in the case of a heating system, if I'm trying to make hot water, I'm using 50-degree groundwater, and I'm making hot water. And if I'm air conditioning, instead of a 95-degree compressor running outside against an expansion device or your condenser, then I'm running 50-degree groundwater. So a heat pump inherently has a coefficient of performance 3 to 5 times that of a conventional system. Now, we go to one further configuration. What if I got rid of the ground loop? Scenario would be you air condition the house as you heat the pool. And you don't need a ground loop. If the pool minimum heating load is 6 kilowatts or 72,000 BTUs, and the house minimum cooling load 72,000 BTUs, I could literally run the heat pump against the pool all day long and only pay for the equipment, and the payback's about 2 years. Commercial application we were involved with this design was Avon, Colorado. There was a hotel that had the core of the building that they need to keep chilled, and the exterior of the building they had to keep warm in the middle of January. And they were having problems with their chilling towers freezing up. And I said, what's your base load? Like, what's the minimum load that runs 24/7 on cooling? And they said it was 6 to 10 tons. And so what we did was simply put a heat pump between their cold chiller loop and their hot loop, and essentially let that thing run 24/7. And if you do it that way, you're still paying the same amount of power, kilowatt hours, for the heat pump to run, in this case 1, and you're getting double the output. So you get a COP of 8. Now let's get rid of the heat pump. This is kind of like the Iowa root cellar. It doesn't cost anything to keep that root cellar chilled. And if I have 2 variable speed pumps at 200 watts apiece, and I can circulate water at 15 gallons a minute, I can get 72,000 BTUs per hour. When you convert that to kilowatts, you basically have 0.4 kilowatts of power, and you're driving 21 kilowatts of cooling. This system's called passive radiant floor cooling, and it basically uses the geothermal ground loop, bypasses the compressor, and basically cools the building. And your coefficient of performance, somebody's phone's ringing.
Mine.
Your coefficient of performance is 100 times higher than your typical outdoor air conditioner. Now, the only downside to this configuration is after several months of doing this, the ground's going to warm up. And so you can't just do radiant floor cooling passively all summer long. That's been my experience, unless you're maybe in northern Montana or something like that. But with this configuration, you can actually bypass the heat pump and get much higher efficiency. Now, the wording on the bottom is critical. The geothermal tax credit, which is 30%, was applied just like the solar energy credit to all geothermal equipment. And until November of 2014, the IRS pretty much let anybody apply the geothermal equipment that they had installed as the basis for their tax credit. Well, in November of 2014, they came out with a letter that basically said, the heat pump and the ground loop count, but not the ductwork distribution system. And the rationale behind that was they said that the Congress definition of geothermal equipment uses groundwater as a thermal energy sink to heat or cool the dwelling unit. And they said after you go through a compressor, the distribution doesn't apply. I think that after that gets challenged in tax court, probably would be reversed. However, in that clarification letter of November 2014, they also said, this is the definition of geothermal energy equipment. They did not say heat pump. And the second question that was asked was it have to be manufacturer certified? And they said no. So when you look at the definition of this system right here, it uses groundwater as an energy sink to cool a dwelling unit, and it does exceed Energy Star requirements. So it would qualify the infrastructure on that radiant floor system for the geothermal tax credit. So this is putting it all together. If you basically have a radiant heating and cooling system, and there's a call from a thermostat for heating or cooling, then control somewhere, switch it from the hot tank or cold tank. And the heat pump's job is just to keep the cold tank or hot tank warm or cold. And the passive radiant cooling bypass just measures the water temperature coming out of the ground. And if it's at a lower temperature than the demand temperature of the cold tank, it just bypasses the compressor and directly goes into the cold tank. This is a system model that we actually have a patent pending on. The U.S. Patent Office has stated to us 2 weeks ago they are going to issue the patent. But this system model is the core for the controls of simplifying the entire process of radiant cooling and heating. If you understand this model right here and you get away from a single tank switchover, which HPX has a control that does that, or you're looking for different types of configurations, we found that the complexity overwhelms the contractor. And so our goal is to take a standard model that we know works, whether it's a 3,500 square foot house or a 36,000 square foot house. This model actually works really well. We have dozens of installations where we've installed it. So radiant cooling is not new. Since 500 AD, they've actually used it. Bjorn Olesen wrote 2 articles in ASHRAE summarizing work that was done in Europe in 2007. And the radiant cooling work in 2007 from Europe is actually the basis for Uperner's radiant cooling design manual. So those charts came out of that. There's a picture of me on the left with Ray Bloom from Denver. Ray's kind of a guy that got me up to speed on hydronics. He's a bit of an expert. But what we did was we took Uperner's CCN system, which was BACnet, and programmed it to do radiant cooling. Unfortunately, Uperner realized that DDC and that level of sophistication on control points and writing sequencer controls was over the pay grade of most contractors. So it was not only difficult to install, it was also difficult to support. Yet radiant cooling continues to have some really great visibility out there. This is Reed's journal as of August of last year. And on the right side are some diagrams from John Siegenthaler. He basically said the perfect control system would be one that did outdoor reset in heating mode. And all of you should know what that is with a boiler. It gets colder outside, the supply temperature gets hotter. But then also in cooling mode, it does a dew point control reset. So you have kind of an indoor reset that based on dew point, I can put chilled water or heated, slightly warmer water based on where the dew point is, which increases or decreases the effectiveness of the radiant floor cooling system. So this psychrometric chart shows the 2 control strategies that you can use. One is it's actually used in the Bangkok airport. Bangkok airport has 1 million square feet of radiant cooling, been in place for about 10 years. And what they do is they maintain the relative humidity via DOAS system at 50%. And then they maintain a supply water temperature at 58 degrees, which is 3 degrees above the 55-degree dew point. If you have the ability to do dew point reset, you have the ability to let the floor cool more effectively whenever the humidity is lower and less effectively. So over time, the actual water temperature changes to provide cooling. My house uses dew point reset, and that uses the CCN system, but it's a little bit more complicated and requires a programmable controller. Not that the contractor ever sees, but it's completely acceptable to use a set point control and use 50% humidity, and then turn off the system and pick it up with air if you can't meet the cooling load of the building. So here's some things that affect you as a contractor when you're installing that's really important that you pay attention to with the client. Is the R value of the floor covering dramatically reduces the cooling capacity of the floor. So using a 60-degree mean water temperature, and it's critical when you read the charts that it's not supply water temperature. If I have a 58-degree supply water with a 4-degree temperature rise in cooling mode, I have a 60-degree mean water temperature. So you gotta make sure you go into the chart the right number. If I have a 60-degree mean water temperature, R0, which is stained concrete or tile, I've got a capacity of 8.4 to about 9 in BTUs per square foot that I can remove in cooling mode. If I have hardwood floors, it's more like 6. And if I cover it with a light carpet and light pad, it's more like 4.4. So if you're planning on 8 BTUs per square foot and the client decides to put down carpeting, you just cut your cooling capacity down in half. On the left side of the screen is the Radiant Cooling Design Manual, and the cover picture is intentional in that it shows the sun shining on a floor. In a system like that, you probably have the ability to remove 20 to 25 BTUs per square foot, and many commercial atriums actually use radiant cooling in that application. Another factor is your floor spacing, your tubing spacing. As I said, you have to use 6 inches on center tubing spaces. 9 and 12 does not work. But here's one real advantage. If you install a radiant floor cooling system at 6 inches on center and you're using a geothermal heat pump, you actually increase the efficiency of the heat pump because I can do the same amount of heating with cooler water. So if you look in the red at the very bottom left, at 12-inch tubing spacing to get 15 BTUs per square foot per hour, I need 110 degree supply temperature. If I decrease that tubing spacing to 9 inches, I can do it with 100 degrees. And at 6 inches, I can heat the water at 93 degrees and meet the heating demand. And if you look in the yellow box on the right, the efficiency of the heat pump goes up 27%. It doesn't like to make hot water. There are some high temperature heat pumps that now be up to 140 degrees. You can use them for snow melt. But for radiant floor cooling applications, you should never exceed 125 degree supply water. And I typically will design for around 100 to 105, which gives me some flexibility. Another thing that you will note in this chart is that the R value is similar to the same effect on heating or cooling as the tubing spacing. So having tubing 6 inches on center is the same as an R value of 1. If I increase the R value of the floor covering to 1.5, that has the effect of putting the tubing 9 inches on center. And if I have an R value of 2, that has the effect of doubling my tubing spacing. So this is kind of a complicated spreadsheet, but this is really what you need to go through as a contractor to figure out what part of your load is going to be handled by your cooling through the radiant floor and what part of your load is going to have to be handled by air. So we're going to go up to the upper left corner and we're going to make the assumption that if I have carpet, I can get 5 BTUs per hour per square foot, and tile is going to be 9 BTUs per hour. So I've listed all my zones from Manual J, my square footage, and then my total zone BTUs per hour right out of Manual J. And if I take the BTUs per hour for that zone and I divide it by the square footage, that gives me my BTUs per square foot. So you'll get an idea. You can see the red numbers in the second column, 22, 18, 27, 19. That's the BTUs per square foot that I can get 6 inches on center with a supply water temperature of 125 degrees. Actually, back up. That's the BTUs I need to heat that space. In the gray area, I shouldn't say gray, it's more like tan, the 27, 26, 29, between 25 and 30 BTUs per square foot, I'm getting pretty close to my maximum supply temperature that I can actually give heat to that floor. A mistake that contractors make whenever they're installing radiant systems is if the system isn't warm enough for the homeowner, they just crank up the boiler temperature. And that's the quickest way to destroy hardwood floors. The National Wood Flooring Association prohibits supply water over 125 degrees. And you'll see here that in bedroom zone 5, I need 33 BTUs per square foot. So in that case, I either need to put some tubing in the wall or in the ceiling or do something else to provide extra heat, or I can get it from my air system if I have that installed, which we do. So then I go to the next column in blue, and that's the BTUs per square foot that I need in the master bedroom all through those zones. Well, I can't deliver 14 BTUs a square foot. I look to the right of that, I can only deliver 9, 8, 4, 11, or whatever. And so what I have to do is I deliver the BTU radiant floor capacity that's possible, which is the upper left yellow box. And then the remainder is what's listed on the chart there, 9, 8, 4, 11, 4. And that's the air system that has to pick up the remaining cooling requirements. Radiant floor cooling has no capacity to remove latent heat. So even though I could remove the heat from the space on a sensible basis, I would end up with a cool room that feels really clammy. So you do need circulating air, and you need an air system to not only mix up the air, but also dehumidify it slightly. The big takeaway on this slide is the duct size on the far right side. Architects love this because with a radiant heating and cooling system, you can get by with 8 by 8, 8 by 10, 8 by 6 inch ducts, which is about the size of your ERV or HRV system to provide ventilation air, and you're not making chases for a 10 by 12 or a 12 by 16 inch duct. So in this situation, in this particular house, my cooling requirement is only 2 tons for an air system instead of 6 tons. Where you're going to run into problems is they don't make that small of air conditioners for super efficient homes. What happens is you get to the point where you have to use a larger air conditioner and it ends up being oversized. And what we do to deal with that is we use a variable speed heat pump. Water Furnace manufactures one. Climate Masters announced one. I think they actually might have it on the market. But the difference between a 2-stage compressor and a variable speed compressor is a 2-stage compressor can only scale back to 66% of its total rating. So if it's a 10-ton heat pump, it can only scale back to 6.5 tons. If it's a variable speed compressor, it can scale back to 20%. So when you look under the total cooling column, which is the next to the last column on the right, that shows you the percentage of the heat pump unit, and you'll see that all of those percentages are within the capacity of a variable speed compressor so that I can provide the perfect amount of air cooling without overwhelming the occupant. This is a typical residence, and there's 3 control points that you need to monitor if you're going to implement radiant cooling. First of all, you have to ensure that the fan's always on. If you're dealing with a heat pump, the water furnace heat pumps actually have a control switch that basically will tell you when the fan is running, or you can possibly take the G signal from a furnace, which is a fan signal, and verify that that in fact is on and it's circulating air continuously. Some people might point out that that uses a lot of energy, but with modern heat pumps, you can actually circulate 300 CFM at 38 watts. So for less than a 40-watt light bulb, you get continuous airflow. So you need 3 votes to make the radiant cooling system go on. 1 is you're circulating air, so I know I'm mixing up the humidity. 2, I need to measure the relative humidity in the space and make sure it's not exceeding 50%. Again, on the water furnace control boards, not promoting them, but they inherently have built into them relative humidity sensors that actually report from the thermostat the humidity to a switch on the control board that you can actually put that in series, and you have that control your radiant floor system, whether it turns on or off. And lastly, you have to look at the supply dew point. So your supply water, you're always monitoring your supply water. I'm going to show you a relay that does this. So it's strapped onto the pipe for your supply water, and it's also calculating dew point in the mechanical room. And if the dew point gets within 3 degrees of the supply water temperature, it turns off the system. There's another way to kind of cheat with that, and that is to use that dew point sensor as a bang on, bang off control for a pump. So it kind of cheap injection pump. You can actually have it inject water till it gets close to dew point, turn it off. What you see on the right side in the hallway is what you would have for radiant floor with hardwood flooring. And those are 12 inches on center spacing with 2 tubes within each floor, between each sleeper there. And the sleepers edge to edge, since they're 2x3s, about 9.5 inches, which is totally acceptable to put a hardwood, 3/4 inch solid hardwood floor. It's not acceptable to put an engineered floor, and you have to be very careful if the client's going to put an engineered floor in that most engineered floors are not certified to go over sleepers. They need something like the left-hand side. Well, as most of you know that have gypcrete or level rock put in, it is not self-leveling, and a lot of the contractors have problems putting flooring on that, and they cover it up with plywood, which causes problems with potentially penetrating the tubing, but also it insulates the floor so radiant cooling doesn't work as well. Upener has, not Upener, but USG Level Rock has an agreement with XL. XL is the largest manufacturer of flooring adhesives in the United States, and they make most of the flooring adhesives under brand names such as Home Depot, Lumber Liquidators adhesive, or whatever. If you use USG self-leveling topping with an XL adhesive, XL and USG will certify that floor for 40 years to not delaminate. So it gives you an option to have your level rock or gypcrete contractor put down a self-leveling floor. And the floor self-levels to a 1/16 of an inch over 20 feet. So it's like latex paint that cures and allows you to get perfectly level floor to put either tile or engineered floor on. The lower left corner is what you would typically see for 6-inch on center tubing. If you're cooling like a utility room that has tile, like a laundry room. And on the left-hand side in the upper corner is our typical control panels that we manufacture. These actually happen to have CCZ, which is Upener's wireless system. The CCZ is not compatible with cooling. It only has heat-only thermostats. But you can add one more thermostat to the system with our controls, and it basically allows you to have room-by-room control and heating if you're running CCZ, but it gives you whole house cooling as one zone if you have a separate thermostat, and it allows you to retrofit a CCZ system, but it's not ideal. What's ideal is to have room-by-room control, and that's what the picture on the left is. This is a 20-zone system that has heating and cooling inputs from the thermostats. And our standard for ease of use and reliability based on challenges that we had with Upener's CCN was a plumber with a number 12 screwdriver should be able to hook this thing up. I would also state that any of you that use Takos VVC controllers, they're pretty easy to understand. You put your thermostats on the top, the zone valves on the bottom, and you hook the pump up on the right side and you're good to go. And that's kind of how this control was designed. On the left is a set point control, so it's going to be set at 58 degrees chilled water temperature. And if you look at the gray box on the left-hand side, the lower right corner, you'll see it looks like a little strap-on sensor. That's just in the picture. That's not actually mounted for use, but that sensor is what you put on your supply water pipe. It's a normally open, normally closed relay that if your supply water starts approaching the dew point, it will turn off the radiant floor system so that you don't get any condensation. So the left side is a set point control. On the right side are black boxes that are options if you wanted to do dew point reset or you wanted to do hot water control or some other options that I'm going to show you. It uses Beckhoff Automation Controller, which is an industrial applications controller for mission-critical applications. It's in no way is it a Windows-based system, which is going to crash or anything else. It's industrial automation to run CNC machines in large factories. And the reason we picked it was not only bulletproof as far as its reliability, but I can add as many slots as I want without adding any wires. Those slots that you see on the right side of the CX9020 actually are input-output slots that plug on like Legos, so I can add more and more slots without wiring it. It just uses a standard bus. We have a project in Texas that has 6 wings. It's 36,000 square foot house. And one mechanical room is 200 feet from another mechanical room. Well, we really don't want to put the control in the upper right-hand corner in every single mechanical room. What we really want is the I/O from those remote mechanical rooms communicating back to the main mechanical room as if it was all hooked together. And you can do that with the module in the lower right corner. You can actually just run a Cat5 cable, and the processor on the top doesn't realize that it's located somewhere else. So if you look at the model that I described on the lower left, I've got the radiant floor, which is number 10 in the diagram. I've got ERV, or dehumidification, which is 42. It's kind of the air coil you see in the middle. The hot tank and cold tank are 80 and 46 in that drawing. And then you have the heat pump, which is number 72 down in the middle, and then the radiant bypass is 76. That can either be through a heat exchanger or it can be direct use of ground fluids, and those ground fluids would be 64 and 66 in that diagram. So if you use that model, then on the right-hand side are all the features that you would get out of that control. You get unlimited zones. You can use standard room thermostats, a $40 thermostat from Home Depot. Standard zone valves or thermal actuators from Cleffy or Honeywell or Fuchner, your favorite manufacturer. Cooling always takes priority because cooling takes longer to affect the temperature inside the building than heating. You're not actually changing the temperature of the floor. You're maintaining the temperature at a set point. So the floor is not allowed to overshoot in heating mode. It also is not allowed to get too cold in cooling mode. But there's only a 4-degree delta T on your cooling water versus your floor temperature. And so your cooling tends to take longer to respond than heating. So you never set a system like this back. You always maintain the temperature. It does an outdoor reset just like a boiler for the hot tank, and it does a dew point reset in cooling mode. It also controls injection. So if you wanted to keep groundwater at 48 degrees in your cold tank, because that happens to be the temperature of the groundwater, you can do injection and maintain the dew point at whatever it's supposed to be based on what the sensor calculated. And as John Siegenthaler said, it'd be great if sensors were included, and in fact, all the sensors are included. They're kind of plug and play. Options that you can put in there is you can actually access the programmable logic controller from Wi-Fi or the internet, so you can actually troubleshoot or look at client systems remotely. But it's really designed to keep it simple, stupid. You put the red arrow up, and that turns up the temperature, and the blue arrow down, and that turns down the temperature. You shouldn't have to think about how it works. I explained the remote zones, how you can do that. It does passive radiant floor cooling, so it can bypass the compressor. If you have one temperature sensor, it actually works with solar differential set point control. So you can have solar panels on there, which is number 68 in that drawing. And then it also will maintain your domestic hot water set point. So if you want to add your domestic hot water to the same control, it'll be able to control that remotely or on the controller, it can do that. And if your client wants to have a DDC system like BACnet, Modbus, or Control 4, they want to know when you're away or you are on vacation, you can actually send those signals out. So this is a commercial clubhouse, but it could be a residential home. It gives you an idea of what this looks like installed. 2 heat pumps on the left work in tandem to heat or cool the tanks on the right. The last heat pump on the right is a little baby domestic hot water heat pump that heats the one tank beside it. This is a clubhouse that has multiple pools and spas, and it actually runs the ground loop from a golf course pond, so it doesn't have a real ground loop. It actually just has tubing in the golf course water trap, and it has 27 to 38 tons of capacity, depends on what time of the year it is. And it also feeds chilled water and hot water to a natatorium desert air unit. So the desert air unit doesn't need an outdoor compressor. And it can do snow melt integrated with a boiler, and that provides backup. But you get an idea of the scale of the panel of the controls compared to the whole system. It ends up a very clean easy to use system. If you go to troubleshoot it, if you don't look at the upper left-hand corner, those red buttons, you can turn it auto off and on. So you have the ability to troubleshoot zones just by turning a switch on the panel itself. So that's it. If you have any questions, I'd be happy to answer them.
I've got a question. Doesn't really pertain to your presentation, but I hope you're familiar with it. Are you familiar with the Drake Landing project up in Canada?
No.
Okay. Drake Landing is a solar home community. It's kind of a district heating system, and they have a vertical borehole well field that Rahal put in. And they'd originally started out with this project, and the intent was to take whatever excess solar energy they had and stick into this vertical bore field and try to boost their aquifer temperatures. And it's evidently a static aquifer because they have achieved static temperatures at the core of their vertical borehole loop field of 180 degrees in the middle of the summer, strictly from the input of all these solar systems. Every house has a 2-panel solar domestic hot water heating system. Once solar domestic hot water is satisfied, then all the additional energy is sent into the district heating system. And each house has individual heat pumps within each individual house so that basically they can draw heat off of the well field, run it through the district loop, and extract or put it into the house or whatever mode they're in. That obviously would not be conducive to your passive cooling system. And in talking to Kerry Smith, I believe it is, with IGSHPA, Kerry was one of the engineers that came out from IGSHPA to meet with us in California when we were working on the code. He said that it's on a shelf, that the aquifer is on a shelf, which is just basically a static aquifer that has absolutely no movement to it whatsoever. And I know that from my experience here in Colorado, our aquifers are moving pretty much through the loop field. Is that a correct assumption in most cases?
It's not always the case. I've seen that I say 1 out of 5 installations. Our patent actually addresses process heat recovery, which is the solar would be an example of that. However, we installed a 3.5 million BTU per hour system here in Colorado, one of the largest residential solar arrays. It was 64 panels. And we found that it wasn't cost effective as compared to geothermal with radiant. And so the first cost we could never really get out of it. And it could be because of our climate. We get big snowstorms in the middle of December and January. So when you need the heat the most, you don't get it. And when you don't need it, you basically have a lot of heat. And the particular client that has this has an Olympic-sized pool. So he actually uses the heat, or in your application, they could use the heat to make the efficiency of the heat pump more effective to make hot water. But what we found is when we look at first costs for solar heating with geothermal, the solar side of it isn't quite as cost effective as it could be. The second illustration I've used for that is that the dairies in Colorado have a cooling load right now, which is 10 million BTUs per day, and they have a heating load for their washes, which is 5 to 7 million BTUs per day. And they're actually looking at whether they use solar or geothermal to augment those dairies, and what they're finding is using dual process heat pumps between the chilled milk and the hot water is a higher payback than using their solar thermal systems. But I think it's going to depend on where you're at on how effective that is.
Yeah, I tell you what, I'm going to enable a couple of mics here. I see I've got some questions. Mr. Albuquerque, you are now enabled, and I'm also going to enable Richard. You're both unmuted, so be careful what you say about me, okay? Richard, you had a question first.
Al, those products, those panels you showed before, you offer all of those? Are readily available?
We do. Yeah, we do offer those. The PLC controller that you saw, let me back up. Can I back up, or I'm not on
Yeah,
that?
no, go ahead.
It's not backing up for me. Okay.
There you go.
All right. So these panels on the upper left we manufacture, and we can make 8 zones, 12 zones, 24 zones. The relay panels on the left we can manufacture. The PLC control on the right side is being tested out in my house right now, so that when we run out of hot water, my wife just throws me in the doghouse.
Yeah.
And we actually modeled that on another PLC last summer and found it wasn't industrial strength. It was kind of a Windows XP platform. But I suspect that in 3 or 4 months, we're going to have the controller on the right and the left fully integrated with a panel like you see in the upper left, and just provide that as a unit.
So these would just, when the dew point reaches X, it would turn off the radiant panels.
It would turn off the radiant supply. So it's kind of like if your floor got too hot, it'd turn it off. My
next question is, why the narrow delta for cooling?
Because you can't. There's been a lot of studies on comfort, and the radiant floor, even in heating mode, has a range. Whether you're sedentary, like old folks' home, or you're walking around like an office, there's a very narrow range between 67 and 69 degrees that they really want the floor. You can't make a floor 64 degrees or people feel chilled. So you've got to keep the floor at a reasonable temperature that provides cooling without making it cold.
In cooling mode, you're talking about.
In cooling mode.
Okay.
Right. In heating mode, it's just like a boiler. You can keep the floor at 72 with 125 degree supply water, and you've got a 30 degree delta T or 40 degree delta T.
Okay. Thank you. Do you guys help in design for large projects also, Al?
Is there another question, or did I miss something?
Yeah, he asked you if you also provide design services for radiant cooling projects.
You're welcome.
Can you hear me, Al?
Would you mute him, Mark?
No, I didn't. He's still able to talk, and I'm not muted. Huh.
I didn't hear the question. It was breaking up really bad.
His question was, do you provide design services for radiant cooling projects?
Yeah, we do. And we actually, can you hear me?
Yes.
Okay. Yeah, it's $1 a square foot. So we do. Yep.
Perfect.
Mr. Abishart, did you have any questions for him?
Oh, I was just curious about the strategy of turning off the water flow when you approach dew point, as opposed to modulating your water temp to keep it below dew point and just changing the mix.
Well, that actually is the two methods. One's the poor man's method, and one uses a PLC. So we actually use a mixing valve with a variable speed pump. So when you look at, trying to make it, my screen's not moving.
What mixing valve?
We actually do injection. We do injection with a variable speed pump, either Velo or Magna 3s. We'll do injection to maintain a set water point, and that's what the PLC does. One thing that was exciting at the ACR show is Danfoss now has a zone actuator where you can set the temperature right on the three-way valve, and it fits the standard EBE module. So you can actually set it at 58 degrees and let the zone valve do the mixing for you without any controls involved with that.
Is that a non-electric or an electric one?
It's electric, but it runs on the 24 volts for the valve.
Okay. Did you want to go forwards or backwards on the slides?
I'm not clear how that would be done. Is it a three-way zone valve then that mixes?
Yes. It uses the return water to mix with the supply water.
So it's a mixing valve?
Yeah, it's a mixing valve, but instead of you having to have a 0 to 10 volt signal or something to figure it out, you just set the temperature right on the valve itself.
The set point valve.
That's a set point valve, yeah.
But that temperature is manually, or you have to turn the knob physically to change it, right?
Right. And I said there's two control strategies. One where you use a set point, And that was a psychrometric chart where I just showed you at 50 degrees, 50% humidity with 55-degree dew point, and you set your supply water at 58. Our control and the ones that we implement in all of our homes use a floating dew point, and that's calculated in real time from the PLC as a black box. So you don't ever see that or know how that works. I mean, it's pretty easy to calculate, but that's actually what's controlling the mixing to the radiant manifold. So
and what mixer is used with that out at PLC?
It's an injection pump, so it's either a Velo or it's going to be a Grundfos injection variable speed pump. So we basically give it a 0 to 10 volt signal to control the downstream temperature, and it has a PID loop that measures the temperature downstream, and it's always modulating that mixing valve to make sure that I keep the temperature 3 degrees above dew point.
Are all these systems outlined in your site somewhere?
What do you mean by that?
Your website?
Yeah, your website.
Our website only has pictures. This is as much detail as we have as a contractor technical presentation.
Okay.
We don't actually, I mean, we have, if you send me an email, I can send you pictures of installations if that's really what you're looking for. It's not a problem to do that. But most clients, consumers looking for this stuff, aren't looking for things that look like a panel in the upper left corner of this slide.
I'm interested in whether it's a mixing valve or a pump or anything. I'm thinking of it as a whole system.
Yeah, so you can do it either way. You can either use it as a mixing valve and control modulate the mixing valve, or you can modulate the injection. So if you have an injection system with a primary secondary loop, then you would use an injection pump. If you have a cold tank going directly into your radiant system, then you would use a modulating three-way valve.
Perfect.
David Shaw, your microphone is now enabled if you would like to ask our guest a question. David, can you hear me? Well, I can read you his question. His question was, a potential customer approached me about a 30,000, hope that's not a typo, square foot building, radiant floor heat with geothermal water and solar thermal as a supplement. Could this control system be used for this project?
Yes, as I mentioned before, our largest client is 36,000 square feet in Southwest Texas. So if you backed up to one of the original slides, or actually backed up to the model doesn't care how big the building is. I mean, whether you have a 30-zone module or a 12-zone module, everything else, the hot tank, cold tank, it's based on your total heat load, whether it's cooling or heating, whether you have 1,000 gallons of storage or 500 gallons of storage or 200. That's math that you do, but the control logic is exactly the same for a small house or a huge residence.
Do you want me to keep going backwards, or am I where you need me?
I don't see anything on my screen. I just see the radiant for a cooling residential home.
Yeah, I see the same screen as well. 38. Yeah. Slide 38 is, there we go.
Okay, so let me see if I can control this.
You're driving.
Okay, all right. So this model, right here, that could be 99 zones, or it could be 4 zones on the upper right. And capacity is, what size pump and what size circulator do I use? Do I break that into 2 separate manifolds or 4 separate manifolds based on what's easiest to get my plumbing run throughout the floors in the building? And then the tank sizing is based on how many BTUs per gallon of water that I need, which basically would be 1 gallon for every 1,000 BTUs of capacity. And then the heat pump's going to be sized to be able to meet your peak load demand. And then what we often do is we'll actually just put a boiler on this loop on the hot tank, which allows us to either heat the radiant with the boiler or the heat pump, or augment the heat pump if we want to downsize the ground loop. Or in the case of snow melt, High temperature heat pumps can make 140 degree water, so we can actually run a boiler with a heat pump. And there's a lot of reasons why that makes a lot of sense. Where a typical heat pump, it'll lock out if you send it too hot of water from the boiler. But the high temperature units don't have that problem.
You know, another question just popped to mind in these system configurations, and you and I both know this guy, and I don't hold him in high regards, but I know of a contractor that installed a ModCon boiler that tied it into the geothermal loop. And when his loop gets too low, instead of firing the boiler and putting the heat directly into the distribution panel, he puts it into the heat pump. I mean, obviously, you're going to maintain a thermal efficiency on that modulating condensing boiler that is peak. But have you ever done anything like that?
Yeah, if you do the math, it's not as efficient. Because the ground can't give me back 100% of my heat. And actually, if it's a good ground loop, if you have great thermal conductivity, I dissipate a lot of the heat in the ground. And so we've actually tried that in a couple of cases just to see what happens. If you go to Platinum Lead Home, LEED, you go to platinumleadhome.com, that's my house. And we've tested things like that because I've always been intrigued by the opportunities to do that. And what we found in actually monitoring BTU production or whatever is the ground actually eats up a lot of our energy. And it doesn't work as well unless we have excess thermal loads, whether it's cooling or heating.
Yeah, that was kind of my thought when I saw it. I thought there'd have to be some means of being able to bypass the loop field in order to keep that energy.
Are you saying somebody has the outlet of the boiler hooked up to the source side of the heat pump?
Yes, you're actually pumping heat into the inlet of the heat pump in order to raise the water temperature high enough to keep the coefficient performance of the heat pump high.
I guess that would give you a little bit of time to thaw out your ground exchanger.
That's actually one situation where you would use it. If you want to intentionally undersize your ground loop, you can put a control on the entering water temperature on the source side to where it'll switch to a boiler if the water, say, gets below 35 degrees or something.
Ooh.
Didn't really come across to me as a good use of energy, but like I said,
that means that the ground loop was undersized, and I'm not a big fan of that.
It's pretty common.
That's the number one problem with geothermal contractors is they undersize the ground loop.
Hey, Mark. Maybe you could use a 55,000 BTU boiler to do a 300,000 BTU house.
Yeah, it's probably been done, Rich. John Cavallo, I just enabled your microphone. I know you had a question due to the fact that somebody else was in control of the board. I couldn't see what it was. Did you want to ask a question? Val? John? Can you hear me? John, do you have a microphone? And evidently he doesn't, or doesn't have a question for you anymore.
You could type it into the text if you don't have a microphone.
Yeah. Any other questions?
If you have any that come up, feel free to send me an email. I'd be happy to respond to it.
Yeah, let me get us through the rest of these slides here and back to the end again so that I can close the show out. I do appreciate you coming out, Al, and I'm sure that, well, by the way, you came close to breaking the record for attendance with this particular show. You were one away from it. If we'd have gotten one more person to participate, you'd have set a new record for the RPA and attendance at these shows, so you did a great job. Thank you very much.
What's the record?
The record was 12, and that was when Siegenthaler and Beam were on together, and we had 11, so you came real close.
That was the first one, wasn't it?
I think it would have been really bad luck or bad chi or something if I broke Siegenthaler and Beam's record, so I'm glad I didn't. Those guys are absolute professionals.
If you guys can see the screen, you'll see who our next guest is, which is Dave Springer with Davis Energy Group. And Dave has actually had a significant amount of experience with the Build America program and the Department of Energy in actually going out and proving the feasibility of high-mass radiant cooling and also low-mass radiant ceiling cooling systems He's worked.
Mark, we don't see any slides. I still see my system diagram.
So while he's doing that, I'll just say that Dave Springer was my RPA instructor in 2002 or something, and was telling us about his radiant cooling experiment he did on his house. And it was all new at the time, and I think, if I remember right, he lives up in Winters, or someplace that's scorchingly hot in California, and he had a 5 or a 6 ton air conditioner on his house, and by putting if I remember right, a 1.5 or a 2 ton chiller outside the back porch and pumping cold water into his floor, he only had to run his air conditioner for 4 or 6 weeks a year or something after that.
It's dry up there, obviously, Kurt?
Most of the time, yeah.
Yeah.
But it's hot. I mean, it's that part of California up there in the Shasta and Redding area. 110 to 114 is pretty normal in the summer.
Yeah, he's up there, Mike McFarland territory.
Too hot for me.
Oh man, no way. Couldn't even deal with it.
Oh, but Rich, it's a dry heat.
Yeah, it's dry heat. That's like everybody around here. Oh, it's just the humidity. Shut up, it's hot.
So, Mark, we now see your desktop. It says Dave Springer.
You can see Dave Springer's?
Yes.
Well, he's a great guy, and as Kurt said, he's been around for a long time. He's actually dealt with some of the people that we've had that have entered some of their houses into our contest that we used to hold for the Showcase Awards. And I think it'll be an interesting conversation, and would invite everybody that has been here to definitely show up and give him your attention and see what he can come up with. Oh, John Cavallo, finally, now that I have control of the screen, I can see he doesn't have a microphone. And his question was, again, is a dew point reset control available as a standalone discrete component? And he didn't catch that. Do you sell just that component by itself, Al?
Not dew point reset, because that requires a PLC. But you can get the PLC with the inputs and outputs as a separate device, but we haven't figured out exactly how to market that. In other words, you don't have to get the radiant zone boards to be able to get the PLC and the outdoor reset controller.
Mm-hmm.
So what you saw on the right-hand side of that one picture, that's a PLC controller that we actually are going to mass produce and have it manufactured as a dedicated controller. So you give us, 3 to 6 months and you'll see it.
So that's this picture that you can see here on the right-hand side.
Right. The right-hand side will be a black box, and it'll be as simple as the 2 red leads go to the hot tank, the 2 blue leads go to the cold tank, and you hook this up for your temperature and this for your humidity, and you turn it on, and it's going to enable an injection pump.
Excellent. All right, well, I don't see any other questions coming down. Let's see, here's one from Harvey. Is 1.23 BTUs per hour per square foot a good average number?
I guess I don't understand the question, because I showed 4.4 on carpet, I showed 7 for hardwood floors, and I showed 9 for tile and concrete. So 1.23 looks really low, unless you got really thick pad.
Pretty slim.
Yeah, and as it pertains to that part of the conversation, I think that every contractor should have that conversation early with the homeowner, because the homeowner has no idea what effect their floor finishes are going to have on either a radiant heating or a radiant cooling system. And you don't know what they're planning on putting down, because it's not on the drawings until it's too late. And you show up and there's 1-inch thick Indian woven rugs all over the floor, and they're complaining that it's not comfortable. Well, duh. Yes, Rich?
Can you go back to that slide where Al's email and his website address is for Harvey? I think he might be could use that right now.
Actually, that website was your home website, not the control and.
Yeah, energyhomes.org.
There's a link on that I think you want.
That's the one.
Energyhomes.org is how you get a hold of me.
Okay.
It doesn't have this level of detail in it. This presentation is the highest level of detail you're going to get, because we just put it together for RPA members.
Okay.
Well, at $1 a square foot, that's cheap for consulting.
I know Harvey's got a project going on right now with radiant cooling, and I think he may have some questions or something, or he may find some of this stuff useful in that project.
Yeah, the biggest project I was involved with was $440 million Barracks project.
Nice.
But I can tell you that the logic and all the control sequences are exactly the same. It's exactly the same.
A building's a building's a building.
I got clarification on Harvey's 1.23 number. He's talking about the heat transfer coefficient differential between the surface temperature in the room. In other words, like with radiant floors, for each 1 degree Fahrenheit difference, we get 2 BTUs per square foot per hour. And he's looking at this 1.23 as an average square foot value based on the heat transfer coefficient and the difference between the room and the pad.
Yeah, so what I'd refer him to is there's radiant design manual and the radiant cooling design manual, because they have all the charts in there for supply water, delta T, and the floor covering. So it's going to vary.
Like so many things in life.
One thing I forgot to mention is that ERVs, HRVs are now required for tight homes over 3 air changes per hour at 50 pascals. Yep. And one great way of selling this is that you're not really installing a duplicate air system. You already have to have ductwork installed for your ERV. So let's use that ductwork to add a little bit of cooling and then install a radiant floor cooling system without additional cost from the air side.
It always helps. It always helps to remove that moisture from the incoming air too.
Yeah, exactly.
All right. Well, again, Al, thank you very much for your time and information. You're an amazing source of information, and I would strongly recommend that anybody that has any questions in regards to high mass radiant cooling, ground source heat pumps, etc., contact Al. I think he can probably do you some good.
Yeah.
And again, thank you to all of our participants that took time out of their lives to come and sit and listen to us for an hour and a half, and we'll see you guys again in about 30 days.
There you go.
All right.
I'll see you.
All right, have a good evening.
All right, good night.